now let me give you, starting following this kind of ideas, let me give you some problem, something to think about, and examples. Examples and applications. So this I'm going to state, I'm not going to prove anything. Suppose you have a particle in dimension 1 that follows this equation, the full Langevin equation. So this is, for example, used, this type of equations, they are used to describe ions inside a channel. So let's start with the Langevin equation. For a particle located at position described by the trajectory x of t. So suppose, for example, you have a membrane of a cell. And then you have what is called the pore of a channel. So you have here, you can have a complicated potential well. So this is as a function of the space, let's say z or x. This is the profile of your potential well. I'll put it in blue. Induced by the molecules, you know, you can have some residue that have all kind of shapes, and you are interested in the question. So this has been worked out for the last 20 years. How ions are going to flow through this structure? For example, what is the flux of ions through a channel, depending on the profile? So for this, you have to solve this equation, and you have to add here a potential. For example, we have to add here plus v prime of x equals 2 gamma w dot. And this potential is the potential that you have here. So you can look at different questions. So one question that came out of this in a very simplified case is called the Albedo problem. So the question is how to calculate the flux, how to compute the flux through a channel. So if you have v, for example, equal to 0, and you have something, an interval 0L, suppose you start with a velocity v0. You push a particle with v0. So the question that people have asked, and I'm not going to solve because this is actually mathematically, technically difficult, is what's the probability that the particle will start with a certain velocity will hit L before it goes back. All right, so this is for zero potential. This is called the Albedo problem. So what is the probability? Find or compute the probability that the time to go to the left, is shorter than the time to go to the right. Condition that at time 0 you start at position x equals 0 and with a velocity that goes inside, positive velocity. Where tau L, this is the first time that the particle hit, let's say, the left. What is left? Left is here. So the first time positive, or let's say define, let's say right, the first time that x of t equals L. And t left is the first time that x of t equals 0. Strictly positive. So, and you go with a velocity, that's why here this is strictly positive velocity, so that if you come back, because you make a loop, you just don't come back immediately. So this is actually a very hard problem to solve. It involves understanding, solving the Fokker-Planck equation in dimension 2 in the variable v, the velocity in the phase space, v and x, and to look at the correct boundary condition. So if you want to do something analytically, here, this is not trivial. It has been looked at and published, there are some results published in the 80s, 86, 89, so 1986, 1989, in Siam Journal of Applied Math. Just to show you that those simple questions can have difficult answers, but so that it's important to have this in mind. So 1986, 1989, and this is from one of the authors, David Livermore. So if you do just a Google search, or you can have these two papers. So what people are doing with this, they try to do simulation. They try to do correct simulations. So for example, what happened when you look at two charges, not one but two? Suppose you have the same configuration, you put two charges in the system. You put two charges. How do you calculate, for example, and they cannot of course pass each other. For example, there are two ions of the same charge, plus and plus, or minus and minus. They enter in here. So if this one is moving, then this one has to be pushed, because it will be pushed due to the electrostatic repulsion plus the potential. So how do you study correlated particles? So the idea is what? Just to use two equations. So again, this is, I'll give, two more examples. And then we will move on to the Ito calculus. So again, I said that I'll do the Ito calculus, I'll do the classic that I used to do in Paris for many years, and then we will move on to the new type of calculation I want to show you with what we said at the beginning with the plan we had. So for what is the flux, how you state the problem, I'm not solving anything yet, just showing to you what the problem is. So if you have two correlated particles in the channels, two correlated particle ions in a channel. So how do we write this? We need two equations. So this is particle x1, particle x2, and we want that x1 never penetrates x2. So x1 minus x2, for example, they can always, we can have this condition that they cannot come too close, which means x1 and x2, they cannot be be more than a. And so now we have two Langevin equation, x1 squared plus gamma, so acceleration velocity, plus we have a potential, so we have the potential of the well, this is the channel, plus the interaction term, x1, x2, equals noise, 2 epsilon gamma w1 dot. We have x2 dot, which is plus gamma x2 plus v prime channel on particle 2, plus the force due to, this is the force due to 2 to 1, and this is the force due to 1 on 2 of x1, x2. And for example, equal noise, 2 epsilon gamma, so we don't have necessarily the same noise. So this is W1 and W2. What is, for example, this V12 or V11 or V21? If it's completely symmetric, then V12 on 1 on 2 or V21, this you can take, for example, what is called the Lennard-Jones force. Lennard-Jones force, which is 1 over r6 minus 1 over r12. So it's a constant, c1 x1 minus x2 power 6 minus a constant. So the constants are known in the literature, x1 minus x6, x2 to the power 12. Okay, so this leads to a correlation. This is very hard, because actually the real space for this is what? If we understood that here, you see, this is the space of velocity that I've drawn here, velocity, and this is position. So x and x dot. So this is 2 dimensions for one particle. If you want to analyze this, in dimension 4, if you want to see the configuration of the particle, for example, in x1, x2, if you impose a condition like this in your simulation, so this is x1, and this is x2. And this is x1 equals x2 when they are at on the diagonal. And now, if they want to be outside this region, so we have to have a band of radius a here, of size a, such that the particle cannot they cannot penetrate this band in this abstract space, otherwise they are too close. And so particle enter at position at so what is the meaning of escaping? For example, if this is position L, if this is position L, yeah, it's not great. Sorry, it's position L and L. You're in the square. So particle x1 should escape here, but if particle x1 is there, particle x2 cannot escape, so it has to go away. So there is, all the time, this creates some correlation. So this is x1, x2, and then on this you have to put the potential of the channel, that is the one generated in blue. Okay, so this is an example of writing a stochastic equation for a coupled system. So we've been seeing what happened for something with no correlation, but a potential well. Correlation, where you have to include this, plus the channel, plus noise. What do you do with this? If it's just equation to contemplate, you say, right, what's the point of doing all of this? Well, I understand this argument. This is what you do, for example, on a simulation. This is the equation that you put on the channel, and you simulate like this. And you can get your statistics. Run 100 trajectory, look at the fraction that arrive to here compared to those who are living, what happened when you add an ion in correlation, and this will allow you to understand your system. This is what people did for 20 years. Understanding this by simulation, by finding the right equation. So, for example, at the beginning, they started with this, and they found that everything went wrong. They didn't put the term here for the acceleration. Although, you could say that in a channel, maybe the Smolokhovsky limit is okay, but it's not, because you're in a very small domain and you're looking at very small time. The time to go through a channel is microseconds. And this is comparable to the time 1 over gamma, which is the time for friction, relaxation in a medium. Okay, so and then I'll give you sorry, I'm lost in the notes. Yeah, and now I'm going to give you so if you're interested in all of this, the classical book about ionic channels, this is written by good biophysicist. This is the book of Bertil Hille, and this is like, the name is Ionic Channels and something, and the latest version is 2001. So you'll have some description of this plus the latest about trying. So it's still going on. So what are the big questions in this field? How do you select? Okay, when you make your pasta, what do you select? when you shake your plate with the hole? What do you select? You select the big stuff, and the small go through. So you select the big ones, right? But now how do you do the opposite? How do you select the small and you let the go through? It's not answered. We don't know. And this is what happened. Some ionic channels. Okay, why people are studying ionic channels? Have you ever heard about ionic channels? Ionic channels are the basis of cell communication between internal and external. This is how they regulate their concentration of ions, of water. You know, we have this aquaporin that regulates the concentration when we have water, salt, and sugar. So it remains an important question. So how do you select, for example, potassium versus sodium? They have the same charge. Some channels can select one, some channels can select the other. The difference is the size. So when can you select the small one? I mean, when can you select the big one and not the small one? One should go, but no, it doesn't go like this. So this is important. This is not solved, and nobody has a clear idea of how to understand, like in a generic manner, this question. This is how people do it by simple elementary stochastic simulations of ions trying to move in a channel, where they try to understand how the pore of the channel, how this pore here of the molecules shape the potential, and you can have also this interaction between. I mean, it can be more complicated, but I don't want to go into more detail. Okay, and the last example I would like to show you is how do you amplify with Brownian motion? So this is now a question in transduction, cellular transduction. So the final application, so this is application number 3. So this was application number 2. Application 2. And this is application 1. So this is important. Now what I'm going to describe here for the process of phototransduction. So you know, I told you, I mean, I'm not sure, did I say that at the first class? That we can see a single photon. So if we can see a single photon, it means that you have one molecule activated and you have a cellular response. How come? Did I mention this? How this is done? It's not simple. It took 50 years, and it's still not fully understood. But there is one step, which is the following. You have a photoreceptor, you look at it, you cut the photoreceptor in 2 parts, and there are discs. And now you look at a disc, and this is a disc that I have projected like this. If a light activates a rhodopsin molecule, it becomes activated. So you have, this is time. This molecule starts to be activated here. It is activated for a random time. Poissonian time. This is not Poisson. And then it is shut down. So this is a time, tau, and you can have a mean time, you know. For the time the molecule is activated, it is performing a Brownian motion. So you have such a Brownian motion. And now, here is the question. There are molecules, let's suppose they are fixed. They can also move by diffusion, and so yeah, and this is a, let's say, so you have a Brownian motion with coefficient of diffusion d, which is fixed. And then the molecule is only activated for this time. That is, afterwards, if it does any Brownian motion, nothing happens. It's only during this random time. And now there are molecules. And each time on the way it meets the molecule with a certain probability, the molecule can be activated. So here's the question for you. After an average such a time, how many molecules are going to be activated? So each time, let's say, this Brownian motion hit this particle, it becomes activated with a certain probability, which we call, let's say, probability of activation. This is known, suppose. So I'm interested in what is the mean number. What is the mean number of activated molecules? Of activated. So we have a population activated molecule. Let's say the population is represented by its density. So you have a population of molecule, let's call it T. And there is a density rho of T. You know the density. Suppose this is known. So how do you do this calculation? Okay, so this is more or less the same. We need the same type of model. We need to have a Brownian motion. And now what we need is, of course, molecule, they have a size, right? So how do we account for the size? We can say that instead of looking at just a trajectory, we can look at a band near this, so we get something like this, right? I mean, I'll do it. So, you know what is the name of this? And so on. You can see this drawing. So this is called the Wiener sausage. It has been introduced by Wiener maybe 70 or whatever years ago. And now this is, so we have a band, which now makes sense. So we have something with a certain size. Let's call the size epsilon, which can reflect, for example, the size of the active part of the protein that is moving. And during a certain time tau, we would like to see what is the surface that is covered. Then the surface covered multiplied by the density of particle will give us some information about the number of particles of the type T that is inside. Right? And then for each one that is inside, there's a certain probability of activation, then we can calculate this. All right? So this is the... You want me to... Let's maybe look at it together, and then I'll finish this example. This will close our example type. So you know how to treat, how to describe the Wiener sausage. So let's call the Wiener sausage what I just described to you, which is this ensemble. This is the ensemble made by all the balls centered at the Brownian motion x of s of radius epsilon when s went from 0 to, let's say, the time that it is activated, capital tau. And you take the measure, the surface associated to this. So this is the Wiener sausage, this is ensemble. And I'm taking the measure, the integrals of the indicating function of this, which give you the surface of this, in whatever unit, meter, meter square, micrometer square, this gives you this quantity. But what is interesting, and this I'm not going to prove it, that in dimension 2, this behaves like pi tau divided by log of 1 over epsilon. Epsilon is the size, pi is pi, and tau is the time. And this is a formula due to Mark Katz from the Feynman-Katz integrals, 1974, Rocky Mountain Journals, for those of you who will look at it after the class. Rocky Mountain Journal. So, and this is for tau small. This is an asymptotic formula. What is nice, of course, is there is a phase of formulation and there is a phase of computation, how you do asymptotic analysis, which I'm not doing here, we will do later on in the class, how you calculate. But for this part of the class is to understand what are the questions, how you formulate them, and what are the tools to address them. Okay, so now we are almost there because we have this surface. So what is the total number, the mean number of, sorry, there is something I haven't done. I have to take the expectation of this over all realization, because you start from here, you have one realization. You start from there, you have another one, and then you average over all of these sausages so that it becomes a deterministic number, right? Otherwise, you have something stochastic. You have a piece of a tube which is stochastic, and then you average over, you take the measure, and now you average over all of this, and this is the result. Okay? This is classical tools in classical probability theory. People are looking at a lot of calculating this, and I'll mention something in a second about this. So what is finally the mean number of the expectation of the number of bound molecules? So this is a random number. Each time you do this, you have a certain number, and you average over realization. So this is this pi tau log of 1 over epsilon multiplied by the probability of activated multiplied by the density, because this is the surface multiplied by density is a number, and this is the effective PAC. This is the probability to activate a molecules after when this is called the rhodopsin, after the rhodopsin molecule, or it's any kind of molecule, the rhodopsin molecules hits it. And this, of course, we have also to average over the time, because if the time here is the random time, Poissonian time, you have to average over your mean Poisson process, and you get tau mean. Okay, so what is wrong with this model? Yeah?
How come the size of the Wiener sausage does not depend on the diffusion coefficient?
The size of the Wiener sausage
does not depend on D.
It should. It should, no? Let me think. If the diffusion constant, yeah, because this is probably assuming that D equals 1. You're correct. There is a diffusion coefficient here somewhere for the pass. So the correct units should be d tau, right?
But the ball is just a surface, right? Yeah.
The what? I'm sorry?
Just a surface, yeah, okay. Then.
This is the surface. This is the surface. So this is, yeah, d tau, correct. So what is wrong with this model now that we've corrected this basic thing? What is wrong? I mean, it's not wrong. We are counting things twice. Because of what? Why are we counting things several times, although it's not in the figure? What is the property of the Brownian motion? If you have a Brownian motion and you simulate it, or what do you observe? Is the Brownian motion doing this? No. It does what? It comes back again and again and again and again. Okay, so now this is something that we haven't taken into account, because we're saying that each time the particle encounters, it activates. But if you come back to the same place, it's already activated, right? And so the real calculation, a calculation that would account much more for reality would mean that I have to discount all of the part of the Wiener process where you have the loops. We should if we want to be efficient, discount all of this and reduce some calculation. But this is quite, this is, for example, mathematically quite difficult to look at what is the distribution of point at where the trajectory comes a multiple number of times given a certain time interval. I'm not going to do it. But this is to explain to you how you do some calculation. This is an example of a process of amplification that occurs everywhere in nature. This is the basis of amplification. That's why I wanted to do this. It has some biological meanings, and it is found almost everywhere. This is how you amplify on the surface of a cell by diffusion only for a certain time. All right? Okay. Now we'll change subject. We'll go back to the Ito calculus. So I said, you want a break? I can give, it's all right. It's a good moment to give you, let's say, 7 minutes break, 10 minutes break, so that we'll do a break and then we'll resume with Ito calculus. I'll do Ito, and then I'll show you how we go to partial differential equation, which I think is important. Again, this is textbook, but it's not necessarily what are the typical presentation of this. All right, so we will do this, the PDEs, the Fokker-Planck, so that those of you who are not familiar with the stochastic processes, you know, now it's clear. And then we will start the analysis of the equation. I mean, right now we show the equation, and then we will see how to analyze them. Okay, break. Physics with a lot of variables, a lot of freedom. So it's not the classical physics that you think about the Newton or a solid. It's particle physics where you have millions of particles that you have to do averaging, that you have to look at what happened of the geometry. So this is a new way of thinking, not classical. I mean, classical in the sense that it's classical physics, but you have to have new ways to understand with the classical tools this new type of physics. If you're interested, there is a Physics Today paper that in the last month, that we wrote about these ideas. It's 1 page or 2 pages explaining that ultimately the new biology, the new mathematical physics in the biology uses the classical physics. But now you have to deal with many degrees of freedom. And this problem of change, how you change scale. Nobody knows how you change scale. How you connect a bath of continuous particle with discrete event. How do you do this connection rationally? How do you analyze it? What is the meaning of electricity? Those are basic questions. They are not answered. And I'm not talking about sophisticated questions. This is the basic comprehension of what is electricity in cells. It's not clear. I mean, to us, which means we don't know. Okay? All right. So this is not part of mathematics. This is what I have shown you now. This is part of what is called modeling. Modeling means how you go from a problem to some equations. The math starts when you do analysis, when you extract information, when you extract solution from equation, or you simulate. This is called modeling, all right? Now I'll go back to math.